Today, I'm going to talk about my PhD research topic. That is issues in peer-to-peer network system. This is a file distributed system, and we want to take advantage of network coding to facilitate to find the optimal solution in the system. And this work is with my two advisors at CALTECH, Professor Ho and Professor Efros, and our co-authors, Professor Medad from MIT and Professor Long from National University of Singapore. So here is a brief outline of today's my talk. So first I'll talk about motivation and problem description briefly, and then talk about our main idea, and we'll provide our LP formulation framework to find the optimal solution in this system, and I will show some examples and for like very flexibility of this system, and finally I will conclude my talk. So here is basic file distribution system. So suppose there is one single server containing a finite file, and there is many peers in the system who demands the same file from the server. If we assume this server client model, that means only server can upload the file to all the users. Then in this case, the server overhead is significant, and therefore the download time is kind of prohibitively large. So as an alternative case, we can consider a peer-to-peer system. In contrast, in this system, all the peers can cooperate each other. So when I receive some part of file, then I can transmit this information to other peers in the system. So using this kind of peer-to-peer system, we can minimize the server overhead and definitely the download time. So there is so many examples of this kind of system. So like a bunch of commercial peer-to-peer system like BitTorrent or Napster, Teller, and as you might know, Skype is also using this peer-to-peer technology. And although these guys do not use network coding system, but it was the beta version from Microsoft. And the name is Avalanche, and they took advantage of network coding in this peer-to-peer system, but they do not service this Avalanche system anymore. So there is so many examples to take advantage of peer-to-peer system. So suppose Microsoft has some like updated patch for security or whatever, then their server cannot handle all these downloads to every guys in the world. So instead, every computer can be, because every computer is connected in the network, so they can still use this peer-to-peer technology. So how to model this peer-to-peer file distribution system? As a beginning step, we consider uplink sharing model. So in this uplink sharing model, as before, one single server contains a finite file, and every peer in the system is requiring the same file from the server. And in this case, uplink sharing means there is only bottleneck for the uplink upload capacity constraint. So suppose we are like a home network user. So then in such case, we are connected to the internet via like an ADSL modem. So in such case, we experience very good download speed, but we do not have sufficient upload speed in the system. This is in general. So the reason why is the end users does not have like much files to upload the system or contribute to the network in general. So in such systems, this download speed is pretty high. So download is not usually be the bottleneck of the system. So we assume this system has experienced the bottleneck only from the upload capacity. So far everything is clear. So since we consider this like upload capacity constraint, we inherently assume this complete graph. Because actually in the long run, we formulate the linear programming formulation. So in the case, we can easily add a link capacity constraint. But at the first step, we do not assume link capacity constraint. And also another reason to not to include this link capacity constraint is for comparison purpose. All the other like previous material in this literature do not assume a link capacity constraint, and they like analytically or heuristically provide the algorithm to find the optimal solution using routing. But they did not use link capacity constraint because in their like problem domain, introducing another constraint makes the problem more and more difficult. But as I will show, yeah, the adding a link capacity constraint doesn't hurt the system, like complex system complexity too much in my case.
So hold on, maybe as well, missed something. So you started off with a downlink model, a classical, a server has a file many people want.
Yes.
And now you're talking about an uplink model?
Exactly.
Maybe
so
say again what the...
Yeah, the reason why is this is a peer-to-peer system, not a server-client system. If I assume server-client system, then I do not have to send anything to the other guys. So I do not have to worry about my small upload capacity. But in this case, we assume a peer-to-peer system. So everyone can download and everyone can upload their files. So in such case, download speed is pretty high. Yes. But in this case, because I can send the file to all the other guys, so the upload capacity can be a constraint. Actually, in the server client model, if the file size is f, and there is like n users, then the finish time, the download finish time of this system is simply n times file size divided by server's capacity. Yes. And if we do not assume this peer-to-peer system, that is the upper bound. But if we have like some non-trivial load capacities, then yeah, we can very significantly decrease the download finish time, yes, which I will show.
So you mean this model that each user can download this file from the server, and they can distribute this file among themselves.
Exactly. So this guy can download file from server as well as from all the other users if that user have file. Yeah. There is some causality constraint.
What are they sending to the server?
Oh, actually, this is kind of complete graph. So yeah, I draw that arrow. But if we solve this problem, the solution doesn't include this flow to the server because a server does not require anything from each node. So this is just like a symbolic arrow in the complete graph.
Sorry, I guess I don't follow.
Okay.
So there is no link to the server really. They don't need to use it if they.
Yes, actually there is a link from this guy to the server, but the optimal solution should not include the flow from this guy to the server, and the actual solution is that.
If one guy downloads the file,
Mhm.
is it download from a specific pair or from multiple pairs on server at the same time?
At the same time, because we do not assume download capacity constraint. So yeah, I can download some part of file from server and all the other guys at the same time. Yeah, at the same time. Yeah, but the file should be different. Yeah, because I don't get the same piece from all the others. Yeah, that is like unnecessary.
And the server has no broadcast capability.
So actually everyone has because everyone has because this is complete web, so everyone has like broadcast things, but actually this is wired network, not wireless network. Yeah, this is wired peer-to-peer network.
So they want upload capacity, but
Mhm.
they don't have any download capacity.
They do not have download
They
capacity.
can download any infinite.
Infinite, infinite rate, infinite speed.
Then why they have to peer-to-peer? Because download is infinite bandwidth, then why they do?
Yeah, download is infinite, but the server has upload capacity. Yeah, so a server has like finite upload speed, upload rate. That is called CS. So download speed, infinite download speed doesn't mean it doesn't take any time. Yeah, because there is parallel. Yeah. So for example, there is like a big bowl. Yeah, big bowl. Yeah, at the bottom, and we pour water from the top. even though the big bar has like infinite capacity to get all the water, yeah, but there is pipe from the top has very small, yeah, like a small capacity. Then yeah, it takes time to get the whole water. If the like upload capacity is infinite and download capacity is infinite, then yeah, this is trivial. Like there is no time to take. Yes. So if like there is a including server, we have this like unlimited capacity CIs. So at some time, this guy want to like send like file size of f, then either take time of like f divided by CI. And we can easily add like a link capacity constraint in the.
You're probably going to go on and show us the optimization problem. Right?
Yes, yeah, I will show it in next few slides. Yeah. Maybe, yeah. So, and one more assumption is peers can stay either stay in the system or leave the system after completing download. So actually, in like peer-to-peer system, the incentive issue is pretty important because even though I want to download some file, yeah, I am reluctant to contribute to the system. Yeah, people are not that altruistic. So for selfish behavior, yeah, we need to consider some incentive protocol, and which I will consider in this formulation as well. So everything is clear in the problem formulation?
No, maybe it'll be fun.
Okay, yeah, I hope so. Yes. So I think yeah, it will come in next few slides. Yeah. So yeah, please wait for a minute. That. So our performance objective is minimize finish time. Yes. So we want to minimize the average finish time. Average means average finish time over all the users, or we want to minimize some other metric. We call it a min. But actually, this min is like since we consider all the peers stay in the system after completing download, to optimize the download finish time, the natural sequence of download finish time is the fastest peer finish at the first time, and the second fastest peer finish in the second time, and the slowest peer finish at the last. Maybe yeah, they can finish all together at the same time. But if we consider minimum average finish time, that might be not the case. So min finish time is we want to minimize the finish time from the fastest one to the latest one in the sequential. The reason why we consider this is for a comparison purpose. Yeah, all the other guys considering routing problem in this problem domain consider this one because this one can be solved in distributed manner and in a sequence way. And some guys insist this solution from a min strategy can achieve a minimum average finish time, but we provide a counterexample for that. Yeah.
Excuse me.
Yeah.
So can you explain why you have the minimum average formulation and also the min formulation, but you don't have the min max?
Oh, we have min max. Yeah, min max is yeah. I didn't include this one because yeah, min max is yeah, very clear. So everyone finished in some sequence, and we want to finish the last guy. Yeah, we want to minimize the download time of the last guy, and that is kind of trivial thing in the linear programming formulation. So basically, we can consider any type of any affine function of t, yeah, t's in the linear formulation. Maybe a convex function as well.
Okay, so in what situation the min framework would be used?
What's that?
In what critical situation?
Oh, so well, what I'm saying is, yeah, min strategy doesn't have very significant physical meaning. Yeah, this is just to develop this minimum average finish time. And this is kind of intermediate step. Yes. So as I said, in the altruistic scenario, everybody stays in the system even after completing download. Yeah, the natural optimized sequence is we want to finish the peers from in the order of from the fastest peer to the latest slowest peer. Because yeah, the fastest peer finish at the very earliest time, then he can contribute the others with his huge capacity. Yeah. In some cases, very like small capacity guy finish at the first time, then yeah, even though he has full file, but he cannot contribute as much as the other guys can. So in the scenario where all the peers stay in the system even after computing download, then this sequence is the optimal one. Yeah. But if we consider like a selfish scenario, peers leave the system after computing download, then this sequence is not necessarily optimal. Yeah.
So I'm having trouble understanding, in this peer-to-peer situation, what you're calling the upload capacity.
Mm-hmm. So,
what is so cap 1 is upload capacity of user 1.
Yeah, this is upload capacity of user 1.
What is it? Like in your network, is it just the rate at which you can transmit to?
Yeah, this is rate. Yeah, I can transmit in the unit time. To any users. Yeah. So
is it the rate to S? But you said you don't use
not to S. Yeah, to anybody. So this is a complete graph. Yeah.
So the model is node 1 has a rate capacity 1 that you can transmit to any other node.
Yeah, any other node.
The same for all the other nodes.
Oh, not same. Yeah, we want the sum.
The sum.
Is it the sum of the octals?
It's the sum.
Yes, the sum is limited. Yes.
So the cap 1 is the sum of the rates.
Not exactly. So suppose the capacity is like 10, and the sum of outgoing link is 100. Then in that case, it takes like 10 seconds, right?
I think he's assuming some
that's
kind of
what
radius type link. The downlink is
on
very fast, but
rate,
uplink
and
is really
say
Yeah.
100 is saying how many bits you're pushing through.
Exactly. So yeah, the amount of amount of flow along each link is like an absolute value, like the magnitude. Yeah, it's just like a bit, and the rate is kind of a bit per second. So it has like 10 BPS, like upload capacity, upload rate, upload speed, and if we want to like transmit like 100 bit, then definitely it takes like 10 seconds. So
No, I think the question was whether the upload capacity is the sum of across all those links.
yes, so the order links, yes. But actually, yeah, I should talk about problem formulation, that it will become more clear, because yeah, I consider the copy of this network as a like time expanded graph, and then this like capacity and the time issue will be clear. So yeah, let me briefly talk about the concept of the network coding. Yeah, maybe someone already familiar with network coding, but yeah, let me briefly introduce what network coding is. So network coding is extend the class of data operation in the network. So in the conventional network, the intermediate node within a network performs just receive and forward, repeat that data packet. But in the network coding system, when a node receives some packets from all the other nodes, then it like mix the data and distribute to its through its downlink. So benefit of this network coding is the first one is throughput gain, or some fewer transmission in the wireless system. I will show one basic example in the next slide, and we can also enjoy the robustness under some unreliable settings. And the drawback is absolutely a complexity issue, because each node should do some like encoding and decoding things in the system. So we have some complexity issue. So here is one very basic example of where network coding can give you throughput. So there is one single server, and in this case, this is not peer-to-peer system, but there is two destination nodes. And these two destination nodes requires the same information A and B. Yes, and in this case, all the link has like unit capacity, and this is unit size data. Then in such case, yeah, this node can either send A or B if we consider routing. Yeah. Then in such case, if this node transmit A data, then this receiver 1 can only recover A only. But whereas this receiver 2 can recover A and B. So the rate is kind of, we can say 1.5. Yeah, we may want to like break this data itself and use fractional routing. Then we can increase the throughput up to like 7/8. But it cannot achieve 2. But whereas in this case, this node mixed data like bit XOR operation A XOR B. If this link transmit A XOR B through this link, then this link can recover both A and B because A XOR with A this bit will result in both A and B. We can recover both, and this one too. It can recover both A and B in this case. So if this node performs network coding like this simple bit XOR operation, then both nodes can recover both A and B. So there is some throughput gain in this example. So actually, yeah, I take advantage of this network coding concept in my framework. So. So now our question is, how do we find the optimal like centralized solution? Yeah, in this problem setting, even though this problem setting is not very clear so far, but yeah, we want to use network coding and formulate a centralized LP formulation. And then we want to consider incentive compiler protocol because this incentive issue is very important in peer-to-peer system. And also, yeah, the question is, does this coding help? Yeah. Yeah, in the previous example, I showed the coding can give you throughput gain. But in this example itself, in my problem domain, yeah, there is no coding gain. Yeah, you think, yeah, why do we use network coding in this system, even though it has no coding benefit? But yeah, there is 2 big issues. The first one is if we do not use network coding in this framework, then to find the optimal solution is prohibitively difficult. Sometimes it is an NP-complete problem. But whereas if we use network coding, as I said, we can solve linear programming formulation, which is polynomial time solvable in problem size. And since, yeah, as I said, since we have no performance gain in the system, we can use this network coding as like a routing solution. Yeah, and I will show that example. So since we can use a network coding solution as a routing solution, we do not have any like complexity or the drawback issue of the network coding in this system. And also we provide some example where network coding has indeed a gain, where the network is changed dynamically. So some nodes join the system and some nodes leave the system abruptly, and someone fails to download or upload things. In such a scenario, we can expect performance gain. That is the kind of robust gain of network coding. Yes. So I hope everything will be clear after this slide. So suppose that we have like 5 nodes in the system. So one node is server node, that is denoted by B0, and there is like 4 destination nodes, 4 peers in the system. So all the like 4 peers, B1, B2, B3, B4, yeah, requires the same file from the B0. Yeah. And we consider this copy of time expanded graph. So each copy of copy of graph is exactly identical in each time step. And we have this red dashed one memory edges. So memory edges have like infinite capacity. So every file you received in this phase is retained in the other next future stages. So in this case, yes, still we have like a node capacity. Each node have like a node capacity. Node capacity is rate, how fast we can transmit to the others. And yes, so that is in this case I call it a V1 to VM. There is like n-1 peers, and V0 denotes the server's capacity. And each phase has a each phase is defined. Each phase is defined as a like time invariant flow. Time invariant flow. So what I mean is, in one phase there is no flow change. So if like there is a flow from like this guy to this guy like 3, then yeah, that is fixed. That flow is not changed. If flow level is changed within a graph, then we go to the like next time phase. So actually, we expect that in this case there are like four peers in the system. Then we can divide the time expanded graph into at least four copies. And in each copy, only one peer can finish download. And it is not clear yet. So in that case, in each phase, only one can finish the download. But in some case, in one phase, 2 or 3 or more peers can finish, right? In such case, like this case, suppose V1 and V2 can finish at the same time, then with the time invariant setting, then in such case, the time duration of this second phase becomes 0. Yeah, that is clear. And also, you might think, yeah, to optimize the finish time of V1, yeah, we may require like multiple phases. But we showed that if we have like m peers in the system, then we need n most m time phases. So are you clear with this like time invariant setting to the system? Yeah, because time invariant thing is very crucial in the understanding of this time expanded graph.
So in each phase, is it just one person transmits?
No, yeah, everyone can. Yes, I can transmit to anyone. So I can transmit my file, some of file to like him and you and her. But
like a half duplex like you transmit
I don't have any constraint. Yeah, at the same time,
arrow is a bidirectional.
At the same time, yeah, you can send me. This is a duplex. Yeah, I don't have any half duplex constraint. Yes, because this is different. So there is no link capacity constraint. So we don't have to worry about like half duplex or duplex issue. Yeah, it depends on only my node capacity constraint. I mean, yeah, on node capacity constraint.
But when you say there are no more than m phase,
yeah.
I think that's obvious, right?
Obvious?
Yeah, no more than m phase.
It can be obvious. It can be obvious, but we have to prove that. Yes, because yeah, actually the one phase means time invariant flow. Yeah, along this. So like I can show example for it.
So this starts though with only one person, V0 having the whole.
Yeah, at the first time V0 has only file, and after this phase, V1 finished the download. So V0 and V1 have a complete file, and V2, V3, V4 have some part of files. Yes, they are not empty. Yeah.
So that notation of is signaling the person's done.
Mm-hmm. Yeah, this is the people who is done with the download.
Yeah. What do you mean multicast? Only V1 is the multicast.
So this graph is only for one file.
So what's that?
This is representing only one file?
Yeah, only one file.
Only one file.
Yes, but the file can be divided into very small pieces. Yes. Yeah. So like.
So the file should be distributed to all the nodes, right?
Yeah, all the nodes. Yes.
V1 is the only multicast thing?
No, V1 is not only multicast one. This like a huge time expanded graph. Yes, in the graph. This is like kind of like it consists of many nodes, right? But this is the destination node. Yeah.
At that page, V1 is.
Yes, but in this time expanded graph, everyone is connected and everyone is connected via this memory edges with these different phases. So in this case, this is not broadcast problem because this guy will not download everything. But this guy is downloading everything, but this guy is not because this guy might not download everything in the first phase. So it becomes a multicast problem.
So this particular expanded graph is representing this min optimization where you
min average, yeah,
at
anything.
every phase. That's why you're finishing someone at every phase.
Exactly.
But in general, if some other objective, you maybe don't finish someone in a phase. You might do it, right?
So this leads me to what is the definition of a phase?
The phase is it consists of time invariant flows. So
right, but
in one phase.
But it seems like you're sort of assuming here that at the end of every phase, one more node.
Oh, actually,
no.
actually that is not true. So this guy can finish in later phase, maybe in like first 5 phases. Yes, there is some like flow changes. So there is like 5 times of flow change. That means we need 5 phases.
Right.
And this guy can finish at the 5th phase, right? And the second guy will phase maybe in 7th phase or 8th phase, and so on and so forth.
So the result is by the time you get to M phases, the result says that all of them have gone.
Exactly. So we proved that if we have like M peers, then we can finish at most M times.
Okay.
The reason why I say that at most is in the first phase, maybe like three guys can finish at the same time. Yeah.
So is this a consequence of somehow choosing a basis in a linear program or something?
Actually, no. Actually, this concept is not. The linear programming does not require this kind of time extended graph. Yes. Yeah. From this setting, we can formulate the linear programming.
The fact that you end up finishing in M phases is not somehow for end users is not somehow something you see as a consequence of your linear.
Oh yes, that's true. Yes. So using a linear programming formulation.
Makes that clear.
Yeah. Using a linear programming formulation. Yeah, I can show we have like M phases, or M plus 1 phases, or like 2 M phases. Yeah, the optimal solution will be same. Yeah, that's how we prove it.
If you had download capacities, could you have again formulated time expanded graph?
Yes.
Or just because you don't have download capacities, you can.
Actually, in the scenario where we have download capacity, we will still use this time expanded graph because everything remains the same. Yeah, this is just a multicast problem. And we know that network coding is beneficial in network multicast problem. So when we have like download capacity or link capacity, we will still have this time expanded graph. The reason why we consider this time expanded graph is we think every guys finish in each phase, and in each phase, yeah, we have like fixed flow allocations.
But each phase can also run simultaneously.
Yeah, simultaneously. So do you mean every phase is kind of continuous?
Yes, and not every phase actually going on at the same time, but some of the phases are finishing earlier, therefore it is the first phase and one is the second phase.
Yeah, exactly. So I'm not sure. Yeah, I understand your question exactly, but yeah, if there is like continuous behavior, like this phase will have like 0 time duration. Yeah. Then this guy will finish at the same time with this guy. Yes. And also, if we consider like continuous continuous flow change, then that means we can divide this time expanded graph as a infinite time expanded graph. But as I said, yeah, even though whatever how many time expanded graph we have, then we can reduce it into like M phases graph.
So the duration of each phase
is
it the result of the
no, it's the variable. Yeah.
This is a control.
Yeah, this is control. This is optimization variable. So it is the result from the epic formulation.
So I have a question. You mentioned that the flow might change in between the completion of 2 downloads. Why would the flow change before some file is complete?
Oh yeah, exactly. So the flow will not cannot be might not change from the first phase. So that means if the flow might not change in the second phase, that means this one can be merged into the first phase. That means this second phase have the 0 duration, and after the first phase, the first 2 guys can finish at the same time.
So it will be at most n times.
And most m different times.
And you're considering that the file can only be shared from one of these nodes when it's completed, or
No. When it receives the part of data, yeah, it can share the part of data to
so it
others.
doesn't need to be complete to be shared.
Exactly. Yes. So, for example, to make this guy finish, yeah, there is two ways. Yeah, only if we concentrate only like this phase, yeah, there is like very many the optimal solution. For example, this one can send exactly the whole file to this guy. Then the duration of this phase will be like file size divided by server's capacity, right? Yes. And different setting is say this guy have like capacity 3, and this guy have capacity 2, and this guy have capacity 1. Yes. Then this guy send some of the information to this guy with his capacity, and this guy can send some of the information to this guy. Yeah, only if it receives the sufficient information from this server, right? So in such a case, the server can send some part of a file to this guy, and they will relay this information to this guy. Then eventually, this guy will finish just at the same time. Yeah, with the case where the server send the whole file to like this guy. But yeah, the results are different because if it distributes the part of file to these guys, then yeah, this guy will the duration of this guy will decrease. Yeah. And duration of like this guy will decrease as well. Yeah. So there is no reason. That is the reason why this guy do not send the whole information to this guy. So depending on their like node capacity, yeah, this server will distribute the file with different rate. So to formulate a linear program formulation, yeah, we have this kind of constraints. So this is, as I said, this is multicast network coding. Within each phase, there is one destination node, and in the whole complete time expanded graph, we have like m destination nodes. So this becomes a multicast problem. So yeah, if you're familiar with network coding, we can consider virtual flow conservation. So virtual flow means in the like multicast network coding, the actual flow go through along this link will be the maximum of virtual flow to all the destination nodes. So for example, we have yeah, in this case we have four destination nodes, right? Then that means we have 4 different virtual flows. Virtual flow means the flow to like each destination, and the flow along each link is the maximum of those 4 different virtual flows. Yeah, that is network coding multicast constraint. And as I said at the first time, we have a node capacity constraint, and the optimization variable will be will be the flow allocation. Yeah, how much flow does it convey along each link? And then and also we have this duration of this phase becomes the optimization variable as well. Actually, this time is calculated from this node capacity constraint and the flow coming from each node. So for example, yeah, the total sum of flow from coming from this V1 is like this one plus this one plus this one plus this one divided by its capacity will be some constant, right? Yeah, some constant. And this guy will have the same thing. The sum of all these like 4 flows divided by its capacity will be some value. And this guy will have that value. And T1 will be the maximum of those 4 values, right? It is clear. Yeah. So that becomes the new variable. So here is the linear programming formulation. So this Fj denotes the virtual flow. So we have m different destination and peers in the system, and each like Fj along He is the virtual flow. Yeah. Towards to that destination, and the x of E is the actual flow along the link E.
online algorithm or offline algorithm?
This is offline algorithm. This is a centralized one.
Okay.
Yes. So when network is given, I mean network is given means yeah, everyone is in the system and everyone has some node capacity. Then we can determine the optimal flow location.
So is that possible for like within like in the middle of this offline, some nodes leave the network? Is that
Yes, I do also consider the case where in the middle of the system, the peers join or peers leave the system. Yeah, I can then in the case, yeah, I can consider like multi-level linear programming formulation. Yeah, but I think yeah, I don't have enough time to include that. So if you have any question, yeah, I will answer that kind of dynamic system. Yeah. So this one becomes the duration of each phase. So this is sum. Yeah. So all the flows coming from one node divided by its capacity is less than the duration of the phase. Yes. And so this one becomes the maximum over all the nodes in that phase. And all the flows should be non-negative. And this is like a flow conservation. So all the flows coming to me and all the flows coming out of me, and the difference should be like file left to me size. And this one includes the memory edge flows. So using this linear programming formulation, we can find all the flow variables along each link and the duration of time and so on and so forth. So we can find the optimal solution.
So essentially, the network coding allows you to
Ignore data identity.
what exactly the data is.
Exactly. So that's the key point of my research. So yeah, let me skip that. This one is just objective function of all different performance metrics. So the thing is, these guys, this paper in 2009, they insist that minimum scheduling achieves the minimum average finish time in the same network setting. But using this linear programming formulation, yeah, we provide a counterexample against this claim or conjecture.
So the claim is for routing.
Yeah, this is for routing.
So
yeah.
for routing means
no network coding. So in this case, yeah, they should consider which guy has some data file, then they should recognize the data identity. So the problem is very difficult. So here is some example. So
so your counterexample has nothing to do with network coding either. Your counterexample is a counterexample.
Our counterexample should be because if we use network coding and they do not use network coding, then we cannot insist our solution is counterexample of theirs. Yes. So so the thing is, even though we find this optimal solution using network coding, using this linear programming formulation, but we can say we can verify this optimal solution can be achieved by routing. So it becomes a routing solution as well. But this is different from their optimal solution, and this is better than their optimal solution. So there is not optimal solution. It's an optimal solution. So this is kind of an example that how hard to find the optimal solution only using routing.
So they asserted this as a proof, a theorem, right?
So actually, first draft in the initial submission from their paper, yeah, it was theorem and proof. Yes, but actually in the final draft, yeah, they changed it as claim. Yeah, and that is not proof. Yes.
I think claim is the same as theorem, whereas conjecture is.
Yeah, but they wrote a claim in their paper. Yeah, but so anyway, yeah, we provide this common example to show they are wrong. So yes, actually, here, this is the example. Yeah, this is like this is mean average finish time. Yeah, how the flow looks like, and this is like mean finish time and how they look like. So in this case, we have like 5 peers and only one single server. And this is the flow, how the flow look like in one phase. So as I said, in one phase, there is no flow change. So flows are time invariant. So for example, I said the file size is 256, and the server capacity is 32. Then yeah, we know V1 can finish only after 8 seconds, right? Yeah, it cannot be done less than 8 seconds. Clear? Yeah, because file size is 256 and server has 32. So in this case, the server cleverly allocates the files to all different file peers instead of sending whole 256 file to like this guy. Yeah. So whatever he chooses, the the duration of the first phase will not be changed. Yeah, but it affects on the like later stages. So it maximizes the flow to all the guys. So like right after this first phase, the second peer already have like 64 information from the server. Yeah, that's a lot. Yeah. Also, V1 can transmit some of data to V2 using its full capacity. And V3 can send some of information to V1 and V2 with its capacity, and so on and so forth. So we can find this the minimum average finish time solution. So when we compare the average finish times from these two different strategies, we show that it achieves the smaller average finish time. Actually, in this example, the difference is very tiny. So someone asked me if that is like due to some numerical error or something. But we can provide some we can disprove their claim some systems. So we can show some example where this difference can be non-trivial. Yes.
So you mean that the greedy algorithm is not optimal?
What is greedy algorithm? The algorithm?
Yeah, for your problem formulation.
Min algorithm? Yeah, min algorithm is not optimal in terms of minimum average finish time. But
So
this
the
is
greedy algorithm is not optimal for the mean average problem, right?
exactly, yes. And their claim was the other paper. Their claim was this greedy algorithm can achieve the minimum average finish time.
Can achieve the optimal.
Yes, optimal.
So
But
how can they prove that?
They could not prove. They could not prove. They tried to prove, but they could not. So this is kind of punchline to disprove their theorem, not theorem, their claim. So actually, this is kind of a brute force way. So once I get optimal the numbers from the LP formulation, I can check the data identity. So the thing is, if this becomes the routing solution, some guys should satisfy causality constraint. So causality constraint means I can send the data only if I receive the data previously. Right. Yes. So I can check this data identity manually for this kind of example. So using this labeling method, systematic labeling method, I can show this LP solution is indeed a routing solution. Does not require coding.
So what changes in your LP formulation when you go from routing to network coding?
That is a good question. Actually, if we do not use routing, then we cannot use this variable x. I mean fj. So if we use routing, then we cannot formulate this linear programming formulation. It becomes maybe
multi-commodity flow.
Yes.
Everything is different.
Everything is different. So we should track all the data where the data comes from. For example, in this case, this guy sent 64 in this case. If network coding is used, then we don't care where this 64 comes from. Because if we use random network coding and we assume sufficiently large field size, operational large field size, then we can achieve this LP solution. yeah, with high probability, almost 1. But if we use routing, then 64 is not just a 64. Yeah, 64 comes from, like 32 comes from source, and like 16 from the like second peer, and 5 from the other peer. So we cannot formulate the formulation in such case. So for the older numbers, we have to check the data identity, where this guy come from. Yes. So the program becomes very intuitive. Yes. So that's the main difference between network coding and routing. So yeah, the thing is, yeah, as I remind you, if you use routing, yeah, to find this optimal solution is prohibitively difficult. Yeah. And this is actually like a minimum weight staying a tree problem in routing domain. So which is an incomplete problem. So let me move on to the incentive comparable protocol. So in this network, yeah, even though I received some file, yeah, I have no reason to send my package to all the other guys because I'm not service provider. Yeah, if I utilize my my own resource, yeah, I have to pay my electricity bill, and I have to pay some money to my internet service provider. So yeah, there is no reason to contribute to the system myself. Yeah, I'm not a service provider. So how can we encourage them to contribute to the system? Actually, in this framework, we do not consider that kind of technology or political issue, but we just have this kind of constraint. So in this example, we have some constant reciprocity constraint, constant. Then that reciprocal constraint means between a pair of nodes, yeah, the flow change percentage difference is upper bounded by this law. So if I send 10 packet to her, then I need to get some packet close to that amount, yeah, from her. Yeah, if this reciprocity constraint is 1, then that means I have to give and take the same amount of information. If I give 10 of information to him, then I should get the same amount of information to him from him. Yes. If we introduce this kind of reciprocity, then how the system performance will look like? Yeah, let me show this graph first. So yeah, definitely, if we have this reciprocity, then we experience the increase of finish time. Actually, this one, this red dash one is.
So what if rho equals 1?
Yeah, rho equals 1 is every pair of peer send and receive the same amount of information
over the lifetime of the experiment.
Yeah, over the lifetime.
Because at the very outset, right? The sources that transmit.
We exclude the source from this consideration. Yeah, because source do not receive anything from the peers.
Right.
Yeah, so we do not include the server in the consideration, but any users, yes, we have on this consideration.
But the reciprocity is not enforced at every stage, or it's just at the end.
That is a good point. So in this case, in this simulation itself, this is performed in each phase. So this is more strict one. But if we can consider accumulated version, as well. But this is strict version.
So this is at every phase.
Yeah, in every phase, the data exchange should be same amount.
And the exchange is between every pair,
Every
or
pair.
between that each node receives as much from everyone else as he gives away.
Oh no, every pair. Yes. Yeah, if I give you 10, I should get back 10, and I give her 5, and I should get 5 back. Yes.
So what does this graph mean? Like if you said there's a big gap, right? What is the gap?
Yeah, actually, this is different scenario. So this one, and so this one and this one is the scenario where the peers leave the system after completing download. So the reason why we consider reciprocity is we assume everyone is selfish, right? Everyone is altruistic, then everyone will stay in the system and everyone will help each other. Then in such case, we have very low download finish time. So if everyone is leave the system, then we insist this like mean insist this reciprocity, then we have this kind of huge increase in download finish time.
So isn't there another graph that is everyone stays and is altruistic, but you don't enforce reciprocity? You should get even lower.
Yeah, actually I didn't include. Oh, that is zero. This one. Yeah. So this one corresponds to the reciprocity.
Yeah, right. So
strict reciprocity, and zero means there is no reciprocity. Yeah. So we have this kind of increase. Yeah. This one corresponds to the case where everyone stays in the system even after completing download. And this one is no reciprocity, and this one is strict.
So the penalty is not so big for reciprocity.
In this case, yeah. But if you have like a huge network, this one is only like how many peers? Yeah, only 5 peers. If we have like more peers and more file size, then this compensation will be
You think the penalty for reciprocity?
Will increase.
Larger?
Yes.
So you've observed that?
Yes, for like 30 peers. Yes.
Well,
So
it seems like it could be the other way around, right? With more nodes, so people leave, but there's other people you can get files, get data from, and you're the one who's done the experiment.
Yeah, like actually, what I'm showing is
It's not intuitive to me that the penalty gets bigger.
actually, for the percentage difference, I'm not pretty sure. I have to check it. But like in absolute value, for sure, increase.
The upload capacity of which one is server and which one is peer?
Of what?
16, 8, 6, 4, 2, 32.
Oh, this is ordering from the fastest peer to the lowest peer, and the last one corresponds to the source node. So the file size is 256, and server has like 32 capacity, and this is ordering from the fastest to the slowest peer.
So what is going to be the finish time without comparison, just server only?
Only server only, so no one. So you mean the 0000 and 32?
Yes.
Actually, there should be the
Server only provides access to the end node.
Yeah, if the server can only provide, then we can easily calculate it. That is like we don't care about reciprocity in such case. Then that is like 256 times 5 divided by 32. So that is like 8 times. That is 40. 40 seconds. Average will be 40 seconds. Not the average. So everyone will finish at 40 seconds. So it's way up there.
So for the leaves, is this simulation curve just for the one snapshot, or you average over?
This is the average. Yeah, average finish time. This is.
So I understand you're starting one before, but is that those matrix that's connectivity in the wireless network becomes here?
Actually, in the wireless system, the problem becomes different. We have to check like interference, and we have some scheduling issues. So in this case, as I said, this is not a half duplex, even half duplex. This is duplex. So whenever I receive the file, I can transmit. I don't care about others. So, but in wireless case, when I receive the file, I cannot send the file. And I cannot send file if my neighbor is sending a file. So there is like a huge difference between wireless case and this case.
Okay, so you will choose which members will leave, which members will stay. You don't care about the connectivity.
Oh in this case, leave. Leave means. I'm sorry, I have to clarify that. So leave means the peers who complete the download. In this case, only peers leave. Is the peer leave who is leaving is only the peers who finish the download. Oh, we have finite file size. We do not have like infinite file. So if they complete the file download from the server, then they just leave the system.
So you mean that you sort of know
we
with
know.
some knowledge that as long as it download file, maybe in the future there's no package sent back.
Exactly. We don't have.
So if we report the reciprocity only in total, do you think there will be a line below all these lines?
Oh, what do you mean? Again?
If the reciprocity is not enforced in every phase, but only at the end of
Yeah, my intuition is it should be less. Yeah, less than this curve. Yeah, because that is less strict. Yeah, that is kind of loose condition. Yes. So yeah, let me skip this dynamically changing network scenario. So in some scenario, yeah, we can enjoy a network coding performance gain. Yeah, some like crazy scenarios, so like this guy disappear or some capacity change. Then we can have yeah, benefit of network coding in system throughput. And this is the result. Like this is like average finish time. Then yeah, this is much less than the routing solution. But yeah, let me skip that. So let me yeah conclude my talk. Yeah, it is maybe elapsed time. Sorry about that. So we formulate a formulation to find the optimal solution in this peer-to-peer file distributed system. And the good thing is we can find the solution in polynomial time of the system size. And in contrast, even though we find the LP encoding solution, but this one does not actually require network coding within the system. So within the system, we do not have any like computational complexity issue or other drawbacks of network coding. So we can very nicely use this network coding. And yeah, which I skipped. Yeah, I do not explain this one, but we have some robust gain in dynamical scenario. So these are very important future directions. So in this example, peer can transmit some information. Yeah. At the same time, it receives the information. But in the real system, it is not true because in actual system, like for example, Ethernet protocol, we have like MTU maximum transmission unit size, like few thousand K or something. So in such case, we need to wait some time to receive sufficient of information, and then we have sufficient information received, then we can transmit to other guys, right? So in such a case, we have this kind of delay model, but currently we can easily formulate a problem using this delay model. But the bad thing is that is the integer programming problem, which is NPR problem. So we are trying to like make a good approximation for this kind of delay buffering model. And we also considering currently streaming scenario. And then yeah, with Singapore University, yeah, we provide our like analytical solution to them, and they test this like optimal solution in their experimental test bed and give us feedback. And yeah, we are collaborating with them on this kind of study. And we also.
So what is their experimental test bed?
So they have like the real system. Yeah, they have not wireless system in here. Yeah, they have like actual system using test bed. So there are some bunch of nodes, like 20 to 30 peers, peer like desktops, and everything is connected by like ADSL modem, yeah, which have like a huge, very comparably large download speed and very limited download speed. Yeah, and then they in the like. In the application layer, they control the like flow rate, yes, and yeah, they try to consider this problem because in such a case there is some like IP like some protocol and network layer protocol and Ethernet protocol things. So you know under that kind of practical setting, this our analytical solution might not be the optimal solution. So we want to see how large is the performance gap between ours and the actual system, and we modify our model using this kind of introducing a buffering delay and so on and so forth. This is our direction right now. Okay, so that's it.